All right, so we're now going to do part 2 of chapter 14, second video in chapter 14. And in this video, we're going to be looking at the concentration and how concentration affects the rate of reaction. So let's start by looking at the reaction between ammonium and nitrite ion. When ammonium reacts with nitrite, it gives us nitrogen gas plus water. Well, we can describe the rate of this reaction using a rate law. And the rate law is going to look like this, that the rate is going to be equal to a rate constant K times the concentration of our first reactant raised to the M power times the concentration of our second reactant raised to the N power. M and N are the orders of the reaction with respect to each reactant, or we usually call it the order in. So like we'll say, is this reaction first order, second order, whatever. We will find that M and N, those orders, the exponents, are usually integers. Now, there are some unusual cases where they are not integers, and we're actually going to see one of those towards the end of the chapter. However, most of the time, it should be an integer. So most of the time, it should be an integer. All right. But in order to calculate M and N, we need to do some experiments or look at some experiments and do the calculations. So when it comes to calculating M and N, so here is our rate law. And we need to, if we're going to calculate M, we want to change the concentration of ammonium ion while leaving the concentration of nitrite ion unchanged. And so here I have some data. Now, just to explain what this data is that we took some initial concentrations for ammonium and nitrite, and we did the initial rates for those reactions for 6 different experiments. So if we look down here, again, our goal, in order to get the value of M, we need to change the concentration of ammonium while leaving the concentration of the nitrite the same. And we'll see in experiments 1, 2, and 3, we leave the concentration of nitrite the same, but we change the concentration of ammonium ion. Well, let's just look at this without doing the math yet. We'll just kind of look at it in a really simple fashion. But when we double the concentration of ammonium, you'll notice that the rate also doubles. When we double the concentration of ammonium again, you'll see that the concentration or the rate doubles again. And that would tell you that the value of M is equal to 1. Now, I'm going to show you the math way of doing that rather than just say, hey, look, it doubled, this doubled. We're going to do this using an equation, but and the way that we do that is that we essentially take the rate law and put the data in for experiment 1 and the data in for experiment 2, and then take the ratio between those two rate laws. So it will look something like this. So rate 2 over rate 1 is equal to K times the concentration of ammonium to the M power for experiment 2 times the concentration of nitrite to the N power for experiment 2. Divided by K times the concentration of ammonium to the M power for the experiment 1 and concentration of nitrite to the N power for experiment 1. This looks like something really complicated, but it's really not. It's much easier than it looks. We're going to take the values that are in the table and put them into this and then solve for M. All right, so here I've shrunk the table down a little bit. Hopefully you can still see it just fine. I've shrunk the table down so that we can we'll have more room for our calculation here. So rate 2, we're just going to take this number, the 10.8 times 10 to the negative 7 and put that in there. Oh, I almost forgot. Since K is a rate constant, so K is a rate constant, and the only thing that changes a rate constant is the temperature. So rate constants don't change unless you change the temperature. So we can cancel those out. So we'll cancel those out. And now we can put the values in. So our rate in experiment 2 is 10.8 times 10 to the negative 7. Our rate in experiment 1 was 5.4 times 10 to the negative 7. So we put that number here. And then here we've got ammonium ion in experiment 2. So come over here. Ammonium ion in experiment 2 is 0.0200 molar. And then raise it to the M power. And then the nitrite ion in experiment 2 is 0.200 molar. We put that there, raised to the N power. Ammonium ion in experiment 1 is 0.0100 molar, so we put that number there, again to the M power. And then the nitrite in experiment 1 is right here at 0.200, again raised to the N power. Now right away, we can cancel out this quantity. 0.2 raised to the N power divided by 0.2 raised to the N power, well, that's equal to 1. So we can cancel those two values out. This divided by this is simply 2. So that is simply 2. And then there's a little trick we can do with exponents. If we have the same exponent, a ratio of two things with the same exponent, we can take the ratio of those things and raise it to that exponent. So we can combine these terms. And of course, 0.02 divided by 0.01 is simply 2. So 2 is equal to 2 to the m. Well, it's pretty obvious. You don't need a calculator here. In order to get the correct value for m has to be 1. And m has to be 1 here. However, sometimes it's not quite as obvious as it is here. Clearly, the identity function, anything raised to the first power, is the same value. But again, if it's not entirely obvious, then there is a trick that we can do using logarithms, and I'm going to show you that trick. So if the order isn't obvious, let's say you've got something that looks like this, and your goal is to figure out what the value of m is. And I do this because I know that sometimes when you sign up for this class, maybe it's been a while since you've done logarithms. Well, that's why I'm doing this. So now what we want to do is we're going to take the logarithm of both sides of this equation, and when we do, we get this. So log of a is equal to the log of b to the m power. All right. Well, one of the rules of logarithms is that we can take this value of m and move it around to the front of that logarithm. And so that gives us this. So log of a is equal to m times the log of b. Well, now we can just divide both sides by the log of b, and that will give us this. So if it's not obvious, then you can take this equation and manipulate it so that you get this. And that is a handy thing to remember. So I'm going to encourage you to remember how to do that. So practice that. All right. Well, let's calculate n in exactly the same way that we calculated m a little bit ago. We want to pick two experiments where we changed the concentration of nitrite ion, but left the concentration of ammonium ion the same. And you'll see in experiments 4, 5, and 6, we've done that. We've changed the concentration of the nitrite ion, but we've left the concentration of the ammonium ion identical. We just have to pick two of those experiments in order to figure out n, and we're going to pick experiments 4 and 5. I usually put the larger value up on top, although you don't have to do that. You don't have to do that. It'll still work if you did it rate 4 over rate 5. But let's go ahead and put those numbers in. again, we can cancel out the rate constant K because the only thing that changes the value of K, the only thing that changes the rate constant is changing the temperature. So we'll put the values in for experiment 5 over experiment 4. So here, rate for experiment 5 over rate for experiment 4. So those are those two values. And then concentration for ammonium for experiment 5 and 4 are both 0.2. So I put those in. And then concentration of nitrite for experiment 4 and 5. So here's 5, there's 4. And those are raised to the n power. Now, of course, we can cancel out that value of 0.2 raised to the m power. So 0.2 raised to the m power. And now we can rewrite this. So this becomes 2. This becomes 2 to the n. And of course, n here has to have the value of 1. So n is equal to 1. So now that we have m and n, we can write our rate law. So now that we have m and n, we can write our rate law. So this is the rate law. So we put those values in for the exponents, and we write the rate law like this. Now, of course, anytime you raise something to the first power, you don't have to put that exponent. So we don't have to put a 1 there. And typically, we won't put a 1 there. So we usually don't write the number 1 when it is an exponent. All right, so there we go. We can just we can write it like that. So this is our rate law. K is our rate constant, and then these are both first order. So we would say that this reaction is first order with respect to ammonium, or sometimes we'll say first order in ammonium, first order with respect to nitrite, and then if you want to calculate the overall order, you just add together all of the exponents. So 1 and 1. So 1 plus 1 is 2. So it is second order overall. So now we're going to spend a little bit of time working on problems related to the rate law, understanding how concentration affects the rate and the rate law. So let's start with number 22. We're going to go to the in-class assignment. All right, so here is number 22. Get our calculator ready here. All right, so we have a reaction where A plus B gives us C, and it obeys the following rate law. Rate is equal to K times the concentration of A squared times the concentration of B. Now I'm going to take this opportunity to point out something. The stoichiometry of your reaction tells you exactly nothing about what the rate law will be. So the stoichiometry will tell you nothing about what that rate law will be. We're going to talk about this a little bit more towards the end of the chapter when we look at something that we call elementary reactions. But for now, don't be tricked into thinking that you could just put first order in A and first order in B, when in fact it's actually second order with respect to A and first order with respect to B. In fact, I just answered part B. We'll get to that in a second. So if the concentration of A is doubled, how will the rate change? Well, there is our rate law. So if we double the concentration of A, since it's squared, when we have 2 squared, that's going to be equal 4. So when we double the rate, we will quadruple, or when we double the concentration of A, we will quadruple the rate. So doubling the concentration of A will quadruple the rate. And again, quadruple just means goes up by a factor of 4. All right, will the rate constant change? And the answer to that is, hopefully you guys have seen all the hints that I've dropped here. The answer to that is no. And the reason is the only thing that will affect the rate constant is the temperature. So the only thing that changes K is temperature. All right, so the only thing that will change the rate constant, the value of that rate constant, will be the temperature. All right, what are the reaction orders for A and B? So it is second order in A and first order in B. Again, the order is you just go over here and look at those exponents, second order in A and first order in B. What is the overall order? All right, so the overall order, we just add those numbers together. So overall order is equal to 2 plus 1, no calculator needed, third order. So this is third order overall. And then finally, what are the units of the rate constant? So for this, I'm going to flip over to the back page for just a moment. And when I flip over to the back page, we're going to do a little sketch here, and just a little table. And this table will tell us what the order is with respect, or the order for it'll tell us what the units of the rate constant are for different orders. So we're going to put overall order, and then here for let's see, so that's overall order, and then for the units of K. All right. Well, it turns out it is possible to have something that is zero order overall. And if it's zero order overall, then the units of K are going to be equal to the units that we have for rate. So it'll be molar per second. Another way we could write that is molar and then seconds to the minus 1. Per second means seconds to the minus 1. Just like x to the minus 1 is equal to 1 over x. All right, if it's first order, then it's going to be 1 over seconds, or we can write that as simply seconds to the minus 1. If it happens to be second order, we can have 1 over molar seconds, or we can write that as molar to the minus 1 seconds to the minus 1. If it is third order overall, and this is the one for this particular problem, if it is third order overall, we'll have 1 over molar squared and seconds, or we can write that as molar to the minus 2 seconds to the minus 1. And then finally, if we want to be generic about this, if the overall order is n, so if the overall order is n, we can write 1 over molar to the n minus 1 times seconds, or we can write that as molar to the 1 minus n seconds to the minus 1. All right. So that is a generalized way of doing this. We had a third order overall, so I'm going to put molar to the minus 2 seconds to the minus 1. So molar to the minus 2 and seconds to the minus 1. All right, so let's look at number 27. All right, so we're going to do number 27 just like what we did earlier. So we've got the iodide ion reacts with hypochlorite. So there's hypochlorite, iodide, like this. So there's hypochlorite plus iodide gives us hypoiodite plus chloride. This is a very fast reaction, and it gives us the following rate data. So our concentration, we've got experiment 1, experiment 2, and experiment 3. our rate law is going to look something like this. So rate is equal to K times the concentration of hypochlorite raised to the M power times the concentration of iodide raised to the N power. All right. So in order to calculate the value of M, we need to change the concentration of hypochlorite ion, but leave the concentration of iodide the same. Well, if we look, experiments 1 and 2 will do that. So we'll do rate 2 over rate 1. So rate 2 over rate 1. And that's going to be equal to K times the concentration of hypochlorite ion raised to the M power for experiment 2 times the concentration of iodide raised to the N power for experiment 2, divided by K times the concentration of hypochlorite to the M power for experiment 1 times the concentration of iodide raised to the N power for experiment 1. Again, this looks more complicated than it is. We just need to put in the values from the table. So we'll put in 2.72 times 10 to the negative 4 over 1.36 times 10 to the negative 4. And then our value for K we can cancel out because K is a constant, and the only thing that changes the rate constant, of course, is temperature. For hypochlorite, we'll put 3.0 times 10 to the negative 3 to the M power, and 1.5 times 10 to the negative 3 to the N power. And then here we'll put 1.5 times 10 to the negative 3 to the M power, and 1.5 times 10 to the negative 3 to the N power. Well, now that we've got that, we can cancel out that 1.5 times 10 to the negative 3 to the N power. And here, if we do this, this comes out to 2. And this comes out to 2 to the M. So therefore, M is equal to 1. Now, that we probably could have figured this out without having to write all of this down, but I do like to go through this process to make it absolutely clear what that value is going to be. So now we want to figure out what N is. Well, to figure out what N is, we need to change the concentration of iodide, but leave the concentration of hypochlorite the same. Well, we'll see that we can look at experiments 1 and 3 for that. So we'll do rate 3 over rate 1 is equal to K times the concentration of hypochlorite to the M power for experiment 3 times the concentration of iodide to the N power for experiment 3, divided by K times the concentration of hypochlorite to the M power for experiment 1 times the concentration of iodide to the N power for experiment 1. Just like what we did before, we can cancel out that rate constant. And then for our rate 3, 2.72 times 10 to the negative 4 over 1.36 times 10 to the negative 4 is equal to 1.5 times 10 to the negative 3 to the M power, 3.0 times 10 to the negative 3 to the N power, divided by 1.5 times 10 to the negative 3 to the M power, and 1.5 times 10 to the negative 3 to the n power. Just like what we did in the other half of this problem, we can cancel out that concentration of hypochlorite to the m power, and then we're going to get 2 is equal to 2 to the n. Again, we don't need the calculator in order to figure this out. That n has to be equal to 1. So we have the exponent for m and for n, and so now we're finally able to write the rate law. This is not the rate law. In order for it to be the rate law, we need to write out the actual equation. So our rate is equal to K times the concentration of OCl minus to the first power, and I'm not going to write that exponent, times the concentration of iodide to the n. To write n, it's going to be 1, so we don't need to write anything there. So that is our rate law. So that is our rate law. Okay, so now we want to calculate what the rate constant is. And the rate constant is, let's see, the rate constant, we'll just solve this for the rate constant. So K is equal to the rate divided by the concentration of OCl minus times the concentration of iodide. And now we just need to pick one of the experiments, put the data in, and solve for K. It turns out that it doesn't really matter which one we pick. We should get the same answer. All right, so for the rate, I'm just going to choose experiment 1 because it's first. So 1.36 times 10 to the negative 4 molar per second. And I'm going to write the units just to show you how the units come out to the units for rate constant that I showed you on the back of this page a little bit earlier. All right, our concentration for hypochlorite in experiment 1 is 1.5 times 10 to the negative 3 molar, and that's to the first power, and 1.5 times 10 to the negative 3 molar, this is for the iodide, also to the first power. All right, so now let's punch the numbers in. 1.36 second EE negative 4 divided by 1.5 second EE negative 3. And then we're going to divide that again by 1.5 second EE negative 3. And you'll see that we get 60.4. We have 2 sig figs, so we're just going to write 60. I'll write that as 6.0 times 10 to the 1. And as far as the units, we've got 1 molar up on top and 2 molars down on the bottom. Sounds like that's going to be molar to the minus 1. And then we have per second there, so we'll have seconds to the minus 1. Well, since the overall order for this reaction is second order, it's molar to the minus 1, seconds to the minus 1. Remember a little bit earlier when we saw second order, so that it'd be molar to the minus 1, seconds to the minus 1. That's just to show you that this is consistent. All right, so now that we've got the rate constant, we want to calculate what the rate is for some concentration that we haven't done yet. So all we have to do is to put in the values. So the rate is equal to our rate constant K, and I'll go ahead and rewrite this. So rate constant times concentration of OCl minus times concentration of iodide, and those are both to the first power. So our rate constant is 60. And again, I'm going to put the units in, molar to the minus 1, seconds to the minus 1. For hypochlorite, we've got 2.0 times 10 to the negative 3 molar. And then here for iodide, we've got 5.0 times 10 to the negative 4 molar. So we'll do 60 times this number times this number. So I'm going to clear all that. We'll do 60 times 2.0 second EE negative 3 times 5.0 second EE negative 4. And here we get 6.0 times 10 to the negative 5. And you'll notice we've got molar to the minus 1, molar, molar. So that's going to give us molar. And then seconds to the minus 1. And that is the typical units that we have for our rate. All right. So now that we've done that one, I want you to pause the video and attempt to do this next one on your own. I am going to do it here in a moment, but I want you to pause it and attempt to do this next one on your own before you watch me do this. So I'm going to give you a chance to pause it. All right. Well, now that you have paused it and you've come back and you've got the right answer, you can watch as I do this relatively quickly. All right, so our rate law is going to look something like this. It's going to be K times the concentration of ClO2 raised to the M power times the concentration of hydroxide raised to the N power. And again, we want to figure out what M and N are. To figure out what M is, we need to change the concentration of chlorine dioxide, but leave the concentration of hydroxide ion the same. Well, we'll see that that happens between experiment 1 and experiment 2. Now, generally, I like to put the larger rate value on top. So for this, I'm going to do rate 1 over rate 2. If you did rate 2 over rate 1, it should still work. So the math works just fine. It may take you an extra step to figure it out. So concentration of concentration of ClO2 for experiment 1 raised to the M power times concentration of hydroxide raised to the N power for experiment 1. Concentration of ClO2 to the M power for experiment 2, and concentration of hydroxide to the N power for experiment 2. All right, so now let's just put the numbers in. So for rate 1, we've got 0.0248 over 0.00276. Our rate constant K cancels out because that doesn't change unless we change the temperature. For chlorine dioxide for experiment 1, we've got 0.06, so 0.060 to the M. For hydroxide, we've got 0.030 to the N power. For experiment 2, we've got 0.020 to the M power and 0.030 to the N power. All right, now that we've done that, we can cancel out that 0.030 and do these calculations. Now, just looking at this right away, it's not entirely obvious what that is, so we'll go ahead and do this. 0.0248 divided by 0.00276. And you'll see the number that we come up there is 8.99. So 8.99. And then here, this is clearly 3 to the M. Now, this is one of those cases where it doesn't come out perfect, but it's pretty close to perfect. You can tell that the value of M should be 2 here. This is because 3 squared would be 9. But if we do the math, M is going to be equal to the log of 8.99 over the log of 3. So I'll do that calculation. So I'll do log of 8.99 divided by the log of 3. And you'll see the number that we come up there, 1.999, and I think everybody can agree that that is close enough that we can call that 2. So the value of m is equal to 2. All right, so now let's do n. Well, for n, we want to change the value, or change the concentration of hydroxide ion while leaving the concentration of chlorine dioxide the same. So we'll see that that works for experiments 2 and 3. So we'll do rate of 3 over rate of 2 is equal to K times the concentration of chlorine dioxide to the m power for experiment 3 times the concentration of hydroxide to the n power for experiment 3. And then K times concentration of chlorine dioxide to the m power for experiment 2 times concentration of hydroxide to the n power for experiment 2. Okay, so now what we want to do is just put the numbers in. I'm going to go ahead and cancel out the rate constant K. And here we'll put in 0.00828 divided by 0.00276. For chlorine dioxide, we've got 0.020 to the m power, and then for hydroxide, 0.090 to the n power. And then 0.020, this is for experiment 2, so to the m power. And then for experiment 2, 0.030 to the n power. All right, clearly we can cancel out the concentration of chlorine dioxide because they're both the same. And now we can do this calculation. So 0.00828 divided by 0.00276. And that gives us 3. All right, for this one very clearly is 3 to the n. Well, no calculator needed for this one. We'll know that n is equal to 1. So n is equal to 1. All right, now that we have m and n, we can now put those in, and we will have our rate law. So our rate is equal to K times the concentration of ClO2 squared times the concentration of hydroxide to the first power. And of course, we don't have to write that as 1. All right, well, now that we have done that, let's calculate the rate constant. And so the rate constant will solve this equation for K. K is equal to our rate divided by concentration of ClO2 squared times concentration of hydroxide ion to the first power. Okay, so we'll put in the values. Again, we can pick any of the experiments. I'm just going to pick experiment 1, and I will put the units in. So 0.0248 molar per second. That's our rate. For the concentration of chlorine dioxide in experiment 1, it is 0.060 molar squared and 0.030 molar to the first power. And you do need to remember to put those exponents in, because if you don't, you're going to get the wrong answer. All right, so 0.0248 divided by 0.06 squared, and then we'll also divide that by 0.03. And so the number we get here, 229.6, we've got 2 sig figs, so we're going to call that 2.3 times 10 to the 2, so 230. Now for the units, we've got 1 molar up on top, a molar squared here, and a molar there. So 1 molar up on top, 3 molars down on the bottom. Sounds like it's time to go to the dentist. So we'll get molar to the -2 and seconds to the -1. Well, as we saw a little bit earlier, this is a third order overall reaction. If it's third order, it's molar to the -2, seconds to the -1. All right, so 2.3 times 10 to the -2, or 10 to the 2, molar to the -2, seconds to the -1. So finally, we're now ready to calculate the rate in this particular situation. And so here, rate is equal to K times the concentration of ClO2 squared times the concentration of hydroxide. So our concentration of chlorine dioxide, so we'll go ahead and put our rate constant in. So 230 molar to the -2, seconds to the -1. Chlorine dioxide here is 0.010 molar squared. We do need to put that exponent in. And then for hydroxide, 0.025 molar, and that's to the first power. So now let's punch those numbers in. All right, so 230 times 0.01 squared times 0.025. And that's going to give us 5.75 times 10 to the -4. However, we only have 2 sig figs here, so we're going to round that to 5.8 times 10 to the -4. As far as the units are concerned, we've got molar to the -2, molar squared, and molar, so that's going to give us molar, and then seconds to the -1. And that's always going to be our units for a rate. All right, well, I'm going to stop this video, and in the next part, we're going to look at something. We're going to do a little bit of calculus. So don't freak out, but we're going to do some calculus. It's really pretty cool. All right,